All right, hello everyone. So today we're gonna um, make a code of the Lagrange interpolating polynomial, and then approximate polynomial using the nth degree Lagrange interpolating polynomial. So um, okay, so the definition of nth degree Lagrange interpolating polynomial is, yeah, we have seen this one last time, but let me go over again. So L n comma k. So here, this is the Lagrange polynomial, and then the subindex n means degree, and then the k is the index of Lagrange polynomial. Okay, so this is defined by x minus x0 times x minus x1 through the x minus x sub k minus 1, and then x minus x sub k plus 1 times through the x minus xn. So we assume that n plus 1 those are given. Okay, so the denominator going to be xk minus x0. I mean, pretty much denominator is pretty much the same as the same form as the numerator, but we replaced the x with xk. Okay, so through the xk minus 1, the xk minus xk plus 1 through the xk minus xn. Okay, so now the theorem 3.2 says that what theorem, let's see, 3.2, I think in the new version, I mean, of the textbook, theorem number could be 3.3. Okay, so now then if x0 through the xn are n plus 1 distinct number, I mean nodes. Okay, so let's say here this is an x0 and then here's an x1. Okay, it's not necessary to be a uniform distance. Okay, so here's x2, here's xk, here's xn. Okay, these are nodes. So now the p of x, and then say p of x, which is the we construct the p of x, f of x is 0, using the Lagrange interpolating polynomial. Okay, 0 x plus 2d f of xn, and then ln comma n of x. All right, so the f of x0 and then f of x1 and f through the f of xn are the function value at nodes. We assume that we know the that function value as specific those value nodes x0 to xn. Okay, and then we once we construct the p of x as like this, then the p of x is the unique polynomial of degree n satisfying the f of xk is equal to p of xk, which means that once you define like this, then the p of, I'll just simplify this one, okay, later. So let me give some space right there. Then p of xk must be equal to f of xk. So, and then for each k, it's going to be 0 through the n. Okay, and then so this p of x, I mean the polynomial of degree n and satisfying this condition is unique. Okay, that's the theorem 3.2. And then P of x, this expression can be simplified as like this. Okay, goes 0 through the n, and then f of xk times ln comma k of x. Now then, l n comma k is of x. Oops, this is equal to pi, and then I goes 0, and then I is not equal to k through the n, and then x minus xi over, and then xk minus xi. Okay. So and then yeah. So now the main objective of today's class is to write MATLAB code for the Lagrange interpolating polynomial. Okay. So see. So last time we we just construct the numerator and denominator of the interpolating polynomial, but I'm sure that you guys forgot about this the code. So let me start over the writing code. Okay, so first one, see the algorithm. Okay, so MATLAB algorithm right there. So first one, input. Okay, so first one we need nodes, right? Node must be given. Okay, so let's say D. So D means D must be the column vector. Okay, so that means x0, x1 to the xn. Okay, so input nodes, and then yeah. So sorry. So let me add one more column, which are function values at each node. Sorry, f of x0, f of x1 through the f of xn. Okay, so D gonna must be what? M plus 1 by 2 matrix. Okay, and then also we need because the reason that we construct Lagrange interpolating polynomial, because we wanna what the construct the P of x, right? Right. So why do we need to construct the P of x? Because we wanna approximate the unknown function f. Keep in mind this function f we don't know. The only thing we know is function value at nodes x0 through the xn. Okay, so now then we want to approximate the f of x using Lagrange interpolating polynomial by constructing the P of x like this. Okay, so now then what? And then we evaluate P at a specific x value and then compare um, the that approximation with exact value of f of x. But okay, so now the x value must be given. Okay, so let's say this is w. Okay, w. Yeah, you can use any letter. Okay, so but the reason that I use it w instead of x, because we already use x right here for nodes, right? So w is also column vector, the column vector. Okay, so it should be, let me use, let's say w1. Okay, w1. Okay, w okay, w1, w Um, okay. W1. Give me a second. Yeah. Let's okay. W1, W2, up to let's say WL. Okay. Yeah. So you can say you can start from the sub index 0. Okay, not 1. But the reason that I start from 1, because as you know, the MATLAB, um, in a MATLAB, the index should start from 1, right? So, okay. So this is going to be then L by 1 matrix, right? W. Okay. Okay. And then output going to be P of W, right? P of W, which means that P of W1, P of W2 through the P of W3. Okay. So what that means? This means that what? That means sigma k goes 0 through the n, and then f of, and then xk, right? And then times ln comma k, and then w1, right? Through k goes 0, so we cannot see that, right? 0, and then n, then f of x k, yeah, k times ln comma k, and then w. Oh, sorry, this should be L, right? WL. Sorry. Okay. So now, here's our input and output, right? So keep in mind this. These are the data structure of input and output. Okay. So the next one, yeah, we start from the function. Okay, the function, and then output must be P. Keep in mind this P is what? L by 1 column vector. Okay, L by 1 matrix. Okay, so this is equal to, let me put name as interpol. Okay, so D comma W. Okay, D is what? D is the m plus 1, m plus 1 by 2 matrix. Okay, so first column represent the nodes, second column represent function value and nodes, and the W is the just x values. Okay, so and the next one, the first one, we need to determine the what uh, the number of nodes and the number of x values. Okay. Excuse me. So determine. Oh, yeah, let me skip writing the comment, okay? Because yeah, I'll show you the code complete the code later. Okay. So let's say m. It's gonna be length of d. Okay. So it means what? It means that m is m plus 1. Okay. So since d is what? D is the m plus 1 by 2 matrix, then the the command length um, return the bigger the number out of the row and number of column. So since m plus 1 must be greater than 2, normally, okay, so m must be m plus 1. The L, give me the length W, okay. And then now we are gonna initialize variables, okay. So the key mind is, first what we have to do is what? We need to figure out what? the numerator and denominator of the Lagrange interpolating polynomial. Okay, I goes 0 and I is not equal to k, and then up through n, and then x minus xi over, and then xk minus xi, right? Okay, so what I'm going to do, see first one numerator. Okay, so new m, we're gonna designate NUM-MAT. Okay, so it's gonna be zeros. Oh, I'm sorry. NUM-MAT is equal to zeros. L comma M. So what's this? So what does the NUM-MAT represent? Okay, actually NUM-MAT represent this is a MATLAB code right there. This is a kind of explanation of each line. Okay, so that's gonna be L. Oh my, let me see. Okay, so let's see L. Oh, yeah. So the first column, NUMAT, the first column gonna be W1, okay, minus x0, and then the first column and second row gonna be W2 minus x1 through the what? WL minus x n. Okay, and then second column gonna be W1 minus, let me see. Oh, yeah, so give me a second. W0. Yeah, this is 0. Okay, I'm sorry, this is 0. And the second column gonna be W1 minus x1, W2 minus x1 through WL minus x1. So each column, we're gonna construct the kind of binomial, right? So W minus x0, W minus x1, W minus x3, and so on. So the last column gonna be what? W1 minus xn, right? W2 minus xn up to WL minus xn. Okay, see. So there's going to be how many columns and row? There are n plus 1, which is m columns, and then L rows. So this is L by M matrix. That's what we're going to construct. Okay, so this is the NUM-MAT. Okay, so the next one is, yeah, right there. And the next one, we're going to construct the denominator, right? So DEM and MAT is going to be zeros. And then M by M. Oh, why this is M by M? All right, so because the DEM and MAT is going to be, so let's see. So, okay. Because in NU and MAT, we pretty much plug in W1, W2 through the WL into the numerator x minus xi, right? But the denominators, we're gonna plug in not W but node, right? xk. Okay, so the first one gonna be x 0 minus x0. Okay, and then the second one, the second row, first row, second column gonna be x0 minus x1 through the xn minus x x0 minus x1. Okay. Give me a second. Yeah, sorry. So can you see that? Yep. And the second row going to be x1 minus x0, and then x1 minus x1. So, and then x1, oh, sorry, xn, right? I'm sorry. x1 minus xn through the what? xn minus x0, and then xn minus x1 through the xn minus xn. So as you can see that the diagonal entry gonna be 0, right? Okay, in the that matrix, DEM-MAT, the matrix is size is gonna be m by m, right? M by m matrix, and the all diagonal entry gonna be 0. Okay, so now then once you constructed these two matrices, then what? The for example, then what? L dn comma okay, say ln comma 1 dw, that's gonna be what? W is going to keep in mind W is a column vector, right? Keep in mind that W is a column vector, right? Then this is going to be W1. I mean, the what? Pi. Give me a second. W1 minus x0 times W1 minus x2. Okay, because the W index is 1 right there. So it means that W1 minus x1 should not be included in the numerator, right? So through the W1 minus xn divided by, oh, sorry, right there. And then, excuse me, then denominator going to be what? X1. I'm sorry, x0 minus oh, x1. I'm sorry, x1. x1. x1 minus x0 times, and then this is 1, okay? This is 1. x1 minus x2 through the x1 minus xn. This is going to be that fraction going to be first entry of column vector of this. Okay, now just do that. Then how can you construct this one? Okay, how can you construct this one from those two matrices? All right, so that's what we have to do, okay, in MATLAB. So now, so keep in mind this. So let me, oh, okay, let me write it down again. So L n comma k of w, that's going to be what? It's going to be column vector, right? So w, I mean pi, I goes 0, and then I is not equal to k, and then n. And then w1 minus xk, I'm sorry, xi over, and then xk minus xi. That's going to be first entry. The second entry going to be pi, I equals 0, and I is not equal to k, and then n. then W2 minus xi over, and then xk minus xi. Okay, so, and so on. And the last entry going to be pi, I goes to 0, and the I is not equal to k in the end. WL minus xi over xk minus xi. This is going to be how many entry right there? L. Okay, pi 1. All right, so to get this one from the NUM MAT and the DM MAT, let's say just binomial matrix of the numerator and the binomial matrix of the denominator. Okay, then I'm gonna do, let's see. All right, so we start from the, definitely we have to use a for loop, right? J goes 1 through the M. Okay, so keep in mind this, M is what? M plus 1. Okay, so since the MATLAB, in the MATLAB we cannot start from the 0 as index. Okay, we see that J should start from 1, not 0. So 1 through the, not N, but N plus 1. Keep in mind this. Now then, okay, so now then first one we need to see right there. So we what first we declared what the size of the those two variable, right? So matrix. Okay, so we have to fill out something. We have to fill out these entry in that variable, and then we have to fill out these entry in that variable. Okay, so to do that, we first start, and then we construct this one. Okay, so for z equals 1 through m, then NUM and then MAT, and then all, you see that? So look at the this matrix. So for each column, what? Look at this, each column. Look at difference between each columns, okay, among the each columns. So W1, W2 through WL, W1 through W2 and WL. Each column, the first in the binomial first what terms are same, right? Equal, right? For each column, right? The only different thing is the second term, x0, x1 through xn. So, and there, yeah, I think, oh yeah, this is better. Okay, then all of the row, okay, and then jth column is equal to W. I told you W is what? The column vector, right? So W1 through the WL. Okay, so minus, and then x0, x1. I mean, first column x0, second column x1 through nth column, mth column. Okay, mth column. Keep in mind this is mth column. Mth column. Okay, the W minus D, right? Keep in mind is what's D? What's D? D was what? D is the what input ln plus 1 by 2 matrix, and then the first column represent what those, right? Okay, so we need that. So D J, okay, J comma 1, first column. Okay, jth row and the first column. Okay, you may wonder that, okay, so W is the column vector. Okay, dj comma 1, this is just a real number. Now how can you subtract the real number from the column vector? In MATLAB, then automatically I mean, just recognize that when you do this, then MATLAB gonna recognize that the difference between two data structures, and then you just MATLAB gonna subtract this real number for each entry of that column vector. Okay, automatically. Okay, so you don't have to worry about that. So now on this, okay, once we got it, then put semicolon. All right, and then what about the denominator? Denominator matrix, okay? Then all of the row, comma, j's column gonna be, you see that here, all of the row in j's column, all of row in j's column. So x0 minus x0, x1. See, the first term in a first column, all the binomials, the first column is going to be x0 through xn, the second column, a second term going to be x0, and the second column, the first term going to be x0 through xn, the second term going to be just x1. You see the pattern, right? So now then this is going to be x0 through the xn, x0 through xn, these are nodes, right? So where's nodes? Input D, right? Or a row and the first column, right? Let me see. Okay, let me see now. Okay, row in the first column. Yep. Minus, and then x0 is going to be minus, and then D, and then J, 1. Okay. So you see that the D and then what colon comma 1, that means what, all of the nodes, right? So this one means x0 through the xn. Okay, and then this one means what? Actually what? J minus 1, right? Xj minus 1. So yeah, this is xj minus 1. Okay. And then one thing that I suggest you that when you write code here, just figure out, just check that whether or not the size of this data structure is equal to the size of that data structure. Okay, so what here the size of that data structure is what? Since NUMAT is a L by M matrix, right? So this is gonna be L by 1 column vector. So this is L by 1 column vector, right? Okay. So now then, is this L by 1? Yes. Why? Because I told you this is a real number and this is the column vector. The size of that column vector W is L by 1. So this is going to be also L by 1. Yeah. So, I mean, how can I? Yeah, just say this is L by 1. Yeah. Now, what about the DMMAT and second line? This is what? M by 1 matrix, right? M by 1 column vector, I mean. The right hand side going to be what? Since the D or colon comma 1, this is going to be the M by 1 matrix. This is a real number. So this is going to be M by 1 matrix. Okay, or M by 1 column vector, whatever. Okay. So now then, okay, and therefore we got this, and then Q minus with this is for loop. Okay, that's a for loop. All right, so we constructed these two matrices, this one and this one. Now what are you gonna do? Yeah, we're gonna do this. You see that? All right. So okay, now let me see. Okay, so let me see. Okay, do I need to second page? Yeah, let me do next page. Okay, so all right, we start from the for loop. Okay, so J goes 1 through M. Okay, so do you understand that here? What I'm gonna do? So give me a second. Mhm. Oh yeah. So now what are you gonna do? W. Yeah. So L the okay, this is L by 1. So now we're gonna construct the this is what actually product, right? So we need to figure out the product of that numerator and the product of this denominator, right? Product of that denominator, a numerator and denominator. Okay. So what I'm going to do is for j is 1 through m. Okay. So then give me a second. I goes 1 through m. Yep. Through m. I goes 1 through m. Yep. Okay. All right. The numerator is equal to 1. The denominator is equal to 1. We start from this. So I just declare a new variable. Okay, num dm. So num gonna be num is gonna be I mean w. I'm sorry. So w. Okay, w minus xi. Okay, and the denominator is gonna be x. Yeah, xk minus xi. I mean product pi product. Okay, so okay. Give me a second. See over here, and then 4. Okay, 4 I goes 1 through the m. All right. So Kim, here, what in the definition of the Lagrange interpolating polynomial? So we're gonna product x minus xi and then xk minus xi for each numerator denominator, except for the case that I equals k, right? So in the for loop, if I is not equal to j, okay, then num, okay, so okay, yeah, let me use k instead of j because I think using k is better than using k to better understand. Okay, k and the I is not equal to k, okay, num is equal to, let me see, then num is equal to num times num matrix j k, oops, k comma I. Okay, so understand that in a num matrix you just multiply the what all all of the entry in a fixed row except for kth column. That's gonna be numerator, right? You see what I'm saying? Okay. You see w1 minus x0 times w1 minus x1 times through the w 1 minus xk minus 1 times w1 minus xk plus 1 times through the x w1 minus xn. Okay, that's this. Okay. Then k right there. Okay. Then the denominator is what? It's going to be DEM times DEM MAT, and then what? Next, let me see. X1. Okay. Yeah, so xk minus xi, give me a second. So in the denominator, DMMAT, similarly what we did in MAT, we multiply the all of entry in a fixed row, okay? So second row, we multiply them, but except for what? Except for the diagonal entry, okay? So, oh, sorry. Okay. So now then, this is gonna be what? K, comma I, okay, and then end, right, and then end. If you don't understand that code, so then we'll see. Give me a second, right here. So back to here. Okay, let me to figure out. Let me just expand this one. Okay, and what is this? This is gonna be W1 minus X. What? W0. I mean, give some specific value into K. Let's say K is just 3. Okay. Then the what first entry of Ln comma 3 gonna be W1 minus X X0, and then W1 minus X. I mean through the X2, and then W1 minus X4. You see that? Through the W1 minus Xn. That's the numerator, and denominator is going to be what? The X3 minus X0 through the X3 minus X2 times X3 minus X4 through the what? X3 minus Xn. Is it? Okay. All right. So now then, where these the binomials in numerator? Right there. See that? W1 minus X0, W1 minus X1 through W1 minus Xn. You see? Okay. And then where is the, the binomial in the denominator? Right there. You see X3 minus, I cannot see that, but see 1, 2, 3, fourth column, there is X3 minus X0, X3 minus X2, X3 minus X3, X3 minus, yeah, you see that? Okay, so we the reason that now you see that while we construct the MAT and DMAT, right? The reason that we constructed those two matrix because to construct the this the fraction. I mean Lagrange interpolating polynomial. Okay, so back to the code right there. Okay, so now the end in here. So this end for if, and then that end for the inner for loop, right? Okay. Now what are you gonna do? Okay, so now then, let me see. Then L. Okay. And then now next one is what? We need to. Oh, I think we need to declare that the Lagrange polynomial. I mean, we need to declare the variable for that Lagrange interpolating polynomial. Okay, so yeah, I think I missed that. I'm sorry. So here, and when we initialize two matrix, let me initialize one more variable L. Okay, L. Sorry, L. This is gonna be zeros. L by M matrix. Okay. So what is this? This is a matrix of Lagrange polynomial at W. What that means? right there, L. So L gonna be L by M matrix, which means that the first column gonna be L n comma 0 W, okay, and the second column gonna be L n comma 1 W, okay, through the L n comma n W. Keep in mind this, since W is what? W is a column matrix, L by 1 matrix. So L n comma 0 W is what? L by 1 column matrix. So this is a column, okay? So this is column. Okay, how many column right there? M, right? So this is M, and then L by M matrix. Okay, L by M matrix, keep in mind this. All right. So now then, oh, yeah. All right, so then L, give me a second. So then L, and then, let me second. Let's see. L by M matrix. Okay. All right. All of rho, comma k is equal to then. Give me a second. Oh yeah. So let me modify the code to be more efficient. Okay. So let's see. Denominators. Okay. Let's say numerator is, let's make this one to vector. Okay. So not one, just ones. And then L, comma 1. So NUM is L by 1 matrix. So here NUM is not just this, I'm sorry. NUM is going to be the column vector. I mean column matrix. So W1, sorry, W1 minus X0 times through the W1 minus X K minus 1, W1 minus XK plus 2 plus 1, okay, through the W1 minus XN. That's the first entry of that in the NUM, okay. And the second entry going to be W2 minus X0 through the W2 minus XK minus 1, then W2 minus XK plus 1 through the W2 minus XN, okay. All right. So now then, the NUN going to be, we have to put dot right there, right? Because, okay, dot, and then NUN MAT, and then all of row in the jth column. Yeah. Okay. So then L all row K gonna be NUM. Okay, and then divided by dot divided by, right? Okay, and then DM. Okay. Yeah. So since the yeah so since the matrix the MATLAB is really uh, good for handling the matrix and vectors, that's why So that makes the code more efficient, but it's kind of more abstract. But okay, so I hope you understand this code. Okay, if you don't get it, just let me know. Okay, so I'm gonna explain about this one in more detail. Okay, so now let's see all there. Okay, and then end. Okay. So what? By the way, what does that mean? Dot multiplication. It means that we multiply the each entry of matrix. I mean, each entry of matrix num by that real number. Give me a second. Yeah. So each entry. How can I say? The each entry of num by each entry of the NUMAT. Yeah, sorry. So what that means? So you know that, right? So for example, for example, 1, 2, 3. For example, 1, 2, 3, and then multiply by 1, 2, 3. This is what? Just 1 square plus 2 square plus 3 square, right? It's kind of up in a product. But if you do this 1, 2, 3, then dot, okay, and then let me see. Oh yeah. So oh yeah, I'm sorry, not this one. If you do this 1, 2, 3, then multiply by 1, 2, 3, you're gonna get error because this is the 3 by 1 matrix and then 3 by 1 matrix. Then MATLAB gonna recognize this multiplication as matrix multiplication. But you see that here, the what in the matrix multiplication, the size of the column in the first matrix must be matched with the size of the row in the second matrix. Since these two sizes are not matched, so we got error. Okay. All right. So, but if you use this one, dot and then product, then it means that we multiply the 1 and 1, 2 by 2, and 3 by 3. So which is 1 square, 2 square, and 3 square. Oops. Okay. So now, yeah, we got it. By the way, back to here, we got this L all of row comma K. Now what I'm gonna do? We construct P, right? What's a P? P of X was what? The sigma, right? And then K, there's K. Now I goes 0 through the N, and then F of X I times L N comma I, right? Of X, right? Okay. Let me see. So, or we can say this is kind of inner product, right? So we can consider this one as inner products. Let's say f of x 0 and then f of x 1 through the f of x n times, right? Okay. Give me a second. The L what? N comma 0 and then x ln comma 1 x ln comma n and x. You see? All right, we can say that. Okay, but here's problems. Actually, what input here? The x is here. X is just one single real number, but we deal with what w. The x value is not just single real number, right? So we evaluate the p at not just one single number, but W, which is a vector, right? This is a big problem, right? So then how can you deal with that? Okay. There's gonna be, let's see, a second. Okay, right there. Okay. Yeah, so anyway. So first one, let's the remind of the data structure of the L. Okay, L is in the variable in the code. L is the what? The L by n matrix. I'm sorry. L is what? L by n matrix, right? I mean this is L by n matrix. So this is going to be L. Okay, n comma 0 of W1, Ln comma 0 W2, and Ln comma 0, and then WL. Right. This is the second column going to be Ln comma 0 1, oops, 1 and the W1, Ln comma 1 W2, Ln comma 1 and WL. Right. So the next, the last one going to be Ln comma 1 and W. Not 1, I'm sorry, n, W1, Ln comma n, W2, the Ln comma n, and WL, right? So, okay, now you see that? Okay, so now then, what? Then P, W1, that's going to be f of x0 through the f of x, and I mean, the inner product of that row vector, I mean, dot product, whatever, dot product of that row vector and that column vector L n comma 0 W1 L n comma 1 and W1 through the what L n comma n W1. You see that here? Actually, this is what? This is the row vector of that matrix L, right? Okay, so now we can say that this is equal to what? F of x is 0. I mean, I'm sorry. So this is equal to actually what? What is this? This is actually what what the second column is. What's the structure of the D? D was the what? Is that D? This is actually second column of the input D, right? So the all of row comma second column, right? But keep in mind, what was it? This is the column matrix, right? We have to transpose this into transpose it so that we're gonna get the row matrix of the. So we put prime. Okay, that's the command, the transpose in MATLAB. And then times. This is what row vector of matrix L, right? So L. Okay, and then the first row and all of columns. All of column. Oops. Okay, but this is row vector, but it should be column vector, so we prime that. Okay, see that? But yeah, there is other way to express. Okay, there is other way to express the that inner product, but okay. So now then we can see this. Then generalize this. Then what? P W what I. This is equal to D, and then all of the row comma 2 prime, and then times L, and then ith the ith row, and then all of ith row and all of columns, the prime. Okay, so then back to the code. Okay, so now it's code right there. So this, so back to right there. So now right there, here, you can see that. Okay. So this is explanation, by the way. I'm sorry, this makes just kind of confused. Sorry. So after end, right there, then d4 I is equal to 1 through the L, and then P of I. Okay. Second P. Yeah. Keep in mind this. What is this? P is what? Column matrix. L by 1 matrix, right? Okay. So since I goes 1 through L, so PI, we calculate PI, so P must be L by 1 matrix. Yeah. It makes sense. This is equal to D, all row in second column prime times L I comma all row columns prime. Okay, it's end. Okay. All right. So I'm going to let me stop here. All right. So I'm going to post the code. Okay. In the Blackboard. Right. Or you can try to write the code. Okay. So next time I'm going to cover what's the error analysis of Lagrange interpolating polynomial. Okay. So all right. Thank you guys. See you next time.